During our discussions in advanced adjustment calculus, we covered trend analysis and we discussed about models and how to assess them. The basic idea is that a model is as good as its predictive power. In this lecture, we will reinforce this concept given as example climate models, with the understanding that I'm going to make a few additional comments to enrich the topic. At the end, you are encouraged to ask questions and engage in the dialogue. Let me start with an old proverb. Predictions are hard, especially about the future. This is supposed to be an old Danish proverb. Some credit this proverb to other sources, but independent on where it comes from, it is true. In our previous lectures, we discussed about the issue of real world and models and the interconnection between them. We basically represent a physical reality by a model built based on physics and of course on test data. And when we have the model, how do we know if the model is good? Well, we have to validate it in the real world. So it's like we have to go to the real world to collect information. We leave the abstract model world and go back to the real world in order to validate the concept. We have to test the model against data, and the reality is that we need not just a good model, we need also good data. And that is what the diagram tries to represent. We need reliable data and a realistic model to get good estimates. Either bad data or bad model will result in bad estimates. As discussed before, there are few things that we must respect. One of them is that we must never correct the data to fit the model. I want to paraphrase American physicist and Nobel Prize winner Richard Feynman. He said something that is worth remembering. He said, "It doesn't matter how beautiful your theory is, it doesn't matter how smart you are, if it doesn't agree with the experiment, it's wrong." So, that means we need to validate the model, and if the validation doesn't work, then we go back and refine the model. How can we assess models? Well, I'm going to show a couple of ways here. One is what we call the leave one out cross validation. Imagine that we have this time series with 6 observations and we want to build a model and validate it. What we do is we remove a subset of observations and fit the model using the remaining points. The points that were removed are then used to validate the model. Okay? This is one way of doing it. Another way is as if we predict towards the past. Let's consider again the same 6 data points and we remove the last 2. We do the fitting with the 4 points and then we make a prediction towards the past using the earlier data to validate the model. Now, let's consider the same data set used to project into the future. We can only use common sense. What do you think would be the best model as contrasted to the data? Let's consider a similar current situation. The information shown in green and blue represent observations. The thin lines represent different models, and the red line represents the mean model values. What do you think? Let us look at what those different symbols really mean. Green and blue represent temperature anomalies derived from 4 different balloon datasets and observations coming from 3 satellite datasets, which is basically an indirect measure of the air temperature depending on the amount of energy captured by the oxygen molecules. The thin lines are what the climate models forecast, and the red line their mean. The models are from CMIP5, the Climate Model Intercomparison Project. The overwhelming majority of models are badly offset. There may be some problems. Some mismodeling may become more apparent if we go back into the past. This slide shows how much disagreement the models have among themselves. They basically have a mismatch of about 3 degrees, which seems to indicate that there are models that would follow better the data set and others that don't, probably most of them. Here's another figure showing basically the same thing, dating to a year ago. All models are plotted 102. Their average is shown in black. There are 3 types of observations. The remote sensing satellite observations in red and blue. In red, the last release from the remote sensing systems, a company located in Northern California, and in blue, another satellite dataset from the University of Alabama in Huntsville. In green, we have the so-called reanalysis, actually the mean of 4 reanalyses. These reanalyses are basically numerical weather prediction models which incorporate any data available, may it be ground temperature, temperature information from aircraft, from balloons, from buoys, from satellite, and assemble it with physical models and are estimated in a huge Kalman filter. We can see that these 3 sets, red, green, and blue, agree very well among themselves. This figure groups each model by their linear trend, left to right, highest to lowest, in units of temperature Celsius per decade. It also presents the trends of the 2 satellite solutions and the one from the reanalysis, using the same colors. The mean trend of the 102 models is shown in black. The highest trend on the left is given by the Geophysical Fluid Dynamics Laboratory, GFDL, coupled physical model CM3. Then we have Environment Canada models, CAN-ESM2, Canadian Earth System models. They are all showing a positive trend in temperature of 0.4 degrees per decade. Okay, then we have mean trend, 0.27 degrees Celsius per decade, and on the right-hand side, we have the trend as predicted by the actual observation sets. We have the RSS showing about 0.2 degrees Celsius per decade, the reanalysis at 0.15 degrees Celsius per decade, and the UAH about 0.12 degrees Celsius per decade. The models that are closest to the data sets are the Russian model INM-CM4, the Japanese model MRI-CGC-M3, and the US GISS-E2R and the FIO-ESM models. We can say that these models fit very well with observations, while the others are basically overestimating the heat. Apparently, the new CMIP6 models are exhibiting even more warming than the CMIP5 models, so it sounds like when we have sufficient model comparisons to produce the CMIP6 plots, the discrepancies seen earlier will be larger. Okay, so if we had to choose a model, I would obviously choose among the ones that are closer to the observations. My personal conclusion is that the models are not perfect, most of them really far away. You might have heard about the Inter-governmental Panel on Climate Change, IPCC, and they actually warned about too much reliance in models in one of their assessment reports. They said, in research and modeling of the climate, we should be aware that we are dealing with a chaotic, nonlinear, coupled system, and that long-term predictions of future climate states is not possible. That implies that all require improvements, and the next IPCC report, which is due in 2022, will have improvements, and for the first time, they include solar particle forcing. That is important because there has been lots of work in terms of space weather, and there are data sets that have been made available. Hopefully, they will explain some of the unexplained features. There are two things. One is cosmic rays. We are bombarded by cosmic rays all the time, and we are protected from this bombardment by the magnetic field of the Earth. There is a theory which has been experimentally proven that indicates there is interaction of cosmic rays with the water vapor contributing with nucleation of high-altitude clouds. So we can think of more clouds, less heat, as more energy ends up being reflected. What I would like to emphasize is that the science keeps progressing. I attend scientific meetings, and there are lots of discussions about improvements, improving data collection, analysis, and improving models. I don't see colleagues in scientific meetings talking about the end of the world or things like that. Now the problem is that the IPCC is not a scientific body, but a political body, and it supports this Agenda 2030 that has to do a lot with taxation and controlling the global energy. The IPCC last year and earlier this year released two special reports. The first one is called Global Warming of 1.5 degrees, in which they embraced the worst scenario, saying what would possibly happen if by 2030 we have 1.5 degrees in increase in temperature. And this year they released a second report based on the worst-case scenario, discussing how that theoretical type of warming would affect air, land, and sea. The problem with the choice of worst-case scenarios is that it serves as fuel for politicians and the junk scientific media, resulting in the issue of climate emergency and its political use. Many started to say, oh, in the next 12 years, it is all over, okay? Well, that's not what the IPCC said. The IPCC released reports exploring worst-case scenarios, but not affirming they will happen. The worst-case scenario does not agree with the measurements. Since the first report was issued in 2018, having 2030 as target, then 2030 minus 2018 equals to 12. So let's create fear for 2030. But then people started to say, oh, no, wait a minute. 12 years is not enough to scare people. So let's make it 18 months. Then came the politicians. Well, there is presidential election in the US next year. We need to scare people earlier than that. Oh, so let's make it less time. What about 40 months? That's all politics, okay? But particularly for me, what I personally don't like is how they scare children. They will not have a future, they say. That is coward and cheap. I go back to Richard Feynman, who said, don't pay attention to authorities, think for yourself. But it seems politicians do not want children thinking for themselves. Too dangerous. At the same time, the Secretary of the World Meteorological Organization, a leading organization in the study of climate, made a statement. Let us read that. WMO Secretary-General warns against climate doomsayers and extremists. The General Secretary of the World Meteorological Organization says that the alarmist narrative on climate change has gone off the rails and criticized the news media for provoking unjustified anxiety. Speaking to Finland's financial newspaper Tulosilama, the journal, on 6 September 2019, Petteri Talas called for cooler heads to prevail, saying that he does not accept arguments of climate alarmists that end of the world is at hand. Dr. Tallers also spoke of the dangers of green extremism. He said, while climate skepticism has become less of an issue, now we are being challenged from the other side. Climate experts have been attacked by these people, and they claim that we should be much more radical. They are doomsayers and extremists. They make threats. And he called for the media both to challenge experts and allow a broader range of opinions to be heard. I found that very good because that was the head of the World Meteorological Organization. Okay? He's not denying anything. He's just saying, well, hold your horses. Now, just a quick discussion on climate models. Climate is controlled by natural variability and human changes. Natural variabilities, we have the solar and cosmic forcing, volcanoes, and the position of the Earth with respect to the Sun, the so-called Milankovitch cycles. Human changes, we have chemical contributions, we have deforestation, and urban heat islands. What happens is that the natural variabilities are not well modeled. For example, contribution from solar flares and coronal mass ejections will end up being added to the human-induced global warming. In other words, whatever is ignored or mismodeled will count as human forcing in the models. The good thing is that there has been more than 700 papers on solar forcing on the terrestrial climate since 2010, and also there are defined these on the solar cycles. So there is need for adjusting the models, which are very heavy on CO2. Currently, when the models talk about space weather forcing, they basically take into account only ultraviolet radiation, upper atmosphere, middle atmosphere, global heating, and the direct absorption. They are leaving all the rest outside. They don't take care of it, so there is a lot of information that can be construed, be incorporated into the climate models, and which hopefully is going to make them more realistic with the new observations and the importance of solar forcing. This figure shows there is a very good agreement with solar irradiance in red, with global mean temperatures in blue. It fits well, and so it accounts for variabilities in temperature. Meanwhile, CO2 emissions keep increasing. The better modeling of space weather climate forcing will result in a more realistic model. Now, this is the same plot for the US. There is something that is very interesting which has to do with sunspot cycles. Since the 17th century, there has been a count of the number of sunspots, even without a clear understanding what they are. But they started to count that, and this plot represents the observation since then. We can see there are variations. Between 1650 and 1700, there are basically no sunspots, and it correlates with what is called the Maunder minimum. It correlates with a period of global cooling called the Little Ice Age. And then we have very clearly these peaks, 11-year cycles, and you can see that they go up and down. There are some maxima and minima, and some of them are very interesting, such as the high correlating with the high temperatures of 1930s and 1940s, and the low in the 1970s, time when some predicted an incoming ice age. Those were natural, short-term variabilities. Remember, it is climate we're talking about. What is happening now is that the number of sunspots are starting to decrease, and the prediction I'm using here comes from a presentation by Irina Kitiashvili from NASA. They're forecasting the maximum number of sunspots in cycle 25 to be equal to 50, and solar scientists are starting to make some inference that we may be going towards a minimum, something that would imply essentially cooling. One explanation would be as we have less protection from the sun, the Earth would be swept by more cosmic radiation, resulting in more high-altitude cloud cover. This slide shows paleogeophysics, variations of temperature from the past until the present. It is interesting to see how much temperature has varied through the centuries. Temperatures are derived from proxies, like ice cores. Looking to the right-hand side of the plot, it is the Holocene, what we call the Holocene optimal. Before the Holocene, it was the Pleistocene, where we see all these up and down zigzags. They are the ice ages. Now, we see the snapshot of the Pleistocene looking at the ice ages themselves. The three profiles come from different ice cores collected in different places. They all basically show the same features. We have the ice age when we have low temperature, and then we have these peaks called interglacials, marking warmer temperatures between ice ages. It is interestingly scary to note that ice ages are the normal. We are actually living in a very good time, and here now is a snapshot of the current interglacial from year 8000 before Christ, BC, until today. We have this variation in temperature, the so-called Minoan warming, 4,000 years ago. Then, 2,000 years ago, there was the Roman warming, followed by the medieval warming, then small variations until the current warming. Now, the thing we have to keep in mind is that all of that variation is natural, okay? Attributing the current warming solely to humans seems a bit ridiculous. Certainly, there may be a man-made contribution, but there is also natural contribution. Overall, it is nature that has been controlling climate, and the possible human contribution is very recent. Now, that's something that we're going to discuss in more detail in Geodesy 2. Since the last ice age, when things start to melt, of course, the sea has gone dramatically up. We talk here about 140 meters of sea level rise, and today's rise are a fraction of that. The words natural and man-made are included on purpose so that we do not forget the natural variations. In Geodesy 2, we will talk about these sea level variations, what caused them and how to monitor them, and the associated uncertainties, something we know lay people do not appreciate the importance of. I know the colleagues who have been working diligently to monitor sea level. What we have today is basically a linear growth of about 3 millimeters per year globally, but it varies around the globe. Can't wait for Geodesy 2. I like to show this figure to show you what constitutes climate variations. It is always important to realize that any human interaction or contribution is very recent. And here's something that is very interesting. Look at the scale. We talk about millions of years going into the past. In black, we have variations of atmospheric CO2. In blue, we have variation of global temperature. You can see the peak there in the Cambrian on the left-hand side. 7,000 parts per million of CO2 as compared to the 400 parts per million we have today. During the Cambrian, we had the greatest explosion of life on Earth. We had more animals and a more flush sea. We had an explosion of life. That is so interesting. Always useful to keep a good perspective in terms of history. I don't think the world is going to end in 12 years. Okay, so, as concluding remarks, there are too much more to be discussed, and we will be discussing more science during Geodesy 2. But for now, as far as estimation is concerned, please keep in mind how to assess the power of a model. Remember that a model is as good as its predictive power. Honor the data. Never alter data to fit the model. As a life lesson, just be careful with those who shout problems to later sell solutions, like the sky is falling by my umbrella. We live on this planet where the temperature rises and falls. We have to keep doing what we have done as a species, which is adaptation and mitigation. Pollution, yes, we have to take care of pollution. We need the air we breathe, the soil we plant our food, and the water we drink. That is our responsibility. I think we have technology to look at that. I honestly don't think we can control the climate. That's what I prepare for you. I end up with a joke. It seems this guy don't believe in sea level rise. Otherwise, he'll not have a mansion by the sea.